Picture the recommendation engine behind Taobao, one of the largest e-commerce platforms in the world, trying to figure out what to show you the moment you open the app. For years, systems like this worked by pattern matching, noticing that people who bought running shoes also bought fitness trackers, and using that co-occurrence to suggest items. But the newest generation of recommenders is trying something more ambitious. They want to actually reason about why you're shopping, not just what you've clicked. And that shift, from correlation to intent, is exactly what the RecGPT series at Taobao has been chasing. This new report, RecGPT-V3, tackles the messy engineering realities of running such a system when you're serving hundreds of millions of users. Let's back up. The first version, RecGPT-V1, put a language model in the loop to genuinely understand each user's intent before recommending items. Version 2 scaled that idea by orchestrating multiple agents that reasoned together. Both worked in production, but running language models over user behavior at Taobao's scale, it exposed three serious pain points. First, the system was stateless. Every time you refreshed your feed, the model reprocessed your entire history from scratch, throwing away whatever it had already figured out about you moments earlier. Imagine a doctor who forgets everything about a patient between each sentence of a conversation and has to reread the entire medical file every time. That's absurdly wasteful. Second, there was what the authors call a tag-to-item bottleneck. The language model would reason about you and output natural language tags like outdoor enthusiast planning a hiking trip, but then a separate retrieval system had to translate those tags into actual product IDs. That translation loses information, like describing a painting over the phone. And third, the chain of thought reasoning that made these models smart also made them slow. Generating hundreds of tokens of explanation per user request simply doesn't fit within the tens of milliseconds a feed refresh allows. RecGPT-V3 attacks all three problems with three corresponding innovations. The first is the memory hub, which gives the system persistent state. Instead of rereading your entire behavioral history every time, the memory hub distills your long-term activity into structured, condensed memory units that get continually updated as you interact with the platform. Think of it as the system keeping a running dossier on you that gets refined over time, rather than rebuilt from raw logs on every request. This alone cuts user modeling computation by nearly 56%, because the heavy lifting of understanding you has already been done and cached in a compressed form. The second innovation is the Hybrid-Modal Foundation Model, which addresses the information bottleneck between reasoning and retrieval. The key idea is to let the language model reason not just in words, but also in what they call Semantic IDs, compact discrete tokens that directly represent items in the catalog. So instead of the model saying, "Recommend hiking boots," and then hoping a downstream retrieval system finds the right ones, the model itself can emit tokens that map directly onto specific product embeddings. The model is trained with a hybrid tokenizer that handles both text tokens and these semantic item tokens in the same vocabulary. And during pre-training, it learns to fluidly move between reasoning in natural language, which brings in open-world knowledge, like the fact that autumn is coming or that a user just had a baby, and grounding in item space, which lets it commit to concrete products. It's a bit like giving a translator access to both languages simultaneously, instead of forcing everything through an intermediate lossy summary. The third innovation, Latent Intent Reasoning, is where the paper gets particularly clever. Chain of thought reasoning is powerful because writing out your logic step by step tends to produce better answers, but generating long text is expensive at inference time. So the authors take the reasoning process and internalize it into a small set of learned latent tokens. During training, the model first learns to produce full verbose rationales, and then those rationales get compressed into these compact latent representations that the model can operate on internally. The clever part is that these latent tokens remain decodable. If you need an explanation for auditing or debugging, you can expand them back into readable text. But at serving time, you skip that expansion. The result is a claimed 200x reduction in output token cost, which is the difference between a system that can serve real-time traffic and one that can't. The training pipeline puts all of this together in stages. There's pre-training of the Hybrid-Modal Foundation Model on massive behavioral and catalog data, so it learns the joint text and semantic ID space. Then there's a post-training phase where the latent reasoning is distilled from the verbose version, using techniques that align the compressed latent path with the outputs of the full chain of thought path. The memory hub is maintained by a separate curation process that periodically updates memory units based on new behavior, deciding what to keep, what to consolidate, and what to forget. On results, the online A/B tests in Taobao's Guess What You Like feed are the real proof point. IPV, which is item page views, went up 1.28%. Click-through rate improved by 1%. Transaction count rose 1.97%, and gross merchandise value climbed nearly 4%. At Taobao's scale, a 4% GMV lift is enormous, and crucially, this happened while cutting end-to-end serving compute by 52.4% compared to V2, meaning RecGPT-V3 uses only about 19% of what V1 required. The paper reports that each component contributes meaningfully in ablations, with the memory hub driving most of the compute savings on the user side and latent reasoning driving them on the inference side. Now the honest limitations. Latent reasoning is a compression, and compressions lose fidelity. The decoded explanations may not perfectly reflect what the model actually computed, which raises interpretability concerns, even though the authors position decodability as a feature. The memory hub introduces a staleness question. If a user's intent changes suddenly, how quickly does the compressed memory catch up? The paper doesn't dwell on cases where the memory representation actively misleads the model. And semantic IDs depend on a stable item tokenizer. When the catalog shifts rapidly or new items flood in, that vocabulary needs constant maintenance. Finally, this is a Taobao-specific deployment, and the gains reflect Taobao's particular user base, catalog structure, and traffic patterns. Looking forward, the bigger message is that language models are moving from being clever add-ons to being the core intelligence layer of industrial recommendation systems, and doing so at costs that actually pencil out. The pattern of stateful memory plus hybrid modal reasoning plus latent compression may become a template for other domains where LLMs need to serve real-time traffic. Now let's walk through some questions you might have after hearing all of this. First, why does compressing chain of thought into latent tokens actually preserve performance? The intuition is that most of the value of chain of thought comes from the model having enough computational depth to work through a problem, not from the specific words it emits. When you distill that reasoning into learned latent vectors, you're keeping the computational substrate while dropping the requirement to serialize it into human-readable text. The model still does the thinking. It just doesn't have to narrate it out loud. Second, what exactly are semantic IDs, and why are they better than just having the models output item names or IDs directly? Semantic IDs are lineage discrete codes, usually produced by something like a residual quantizer over item embeddings, so items with similar meanings end up with overlapping code prefixes. Raw item IDs are arbitrary numbers with no semantic structure, so the model can't generalize across them. Text names are semantic, but ambiguous and verbose. Semantic IDs give you the best of both. They're compact tokens that carry meaningful structure the model can learn to compose. Third, how does the memory hub avoid becoming stale or accumulating errors over time? This is a real risk. The paper's approach is to treat memory curation as an ongoing process where new behavior can update, override, or consolidate existing memory units rather than just appending to them. So, if you were shopping for baby products 6 months ago, but now you're shopping for hiking gear, the curation process is supposed to reweight or retire the old memory. Whether this works robustly under fast intent shifts is one of the areas where I'd want to see more stress testing. To bring this back to large-scale recommendation systems more broadly, the 3 ideas here map almost directly onto pain points that anyone running production ranking or retrieval at billion-user scale will recognize. The memory hub concept, maintaining compressed, continually updated user state instead of recomputing from raw event logs, is directly applicable to user tower architectures where sequence models today reprocess long behavior histories on every request. Caching a distilled user representation and only incrementally updating it could dramatically cut serving cost while preserving quality. Semantic IDs are already being explored in generative retrieval systems, and this paper reinforces that letting a reasoning model emit item tokens directly, rather than routing through a text intermediate, closes a real information gap between understanding and retrieval. And latent reasoning is perhaps the most immediately transferable idea. Any team trying to deploy LLM-based ranking or candidate generation runs into the token cost wall almost immediately. Compressing chain of thought into a small number of learned latent tokens while keeping a decode path for offline auditing is a practical recipe for getting LLM quality reasoning into a latency budget measured in tens of milliseconds. That combination, smart offline, cheap online, and inspectable when you need it to be, is exactly the shape production recommendation systems need.